The Doppler effect. You probably heard about this. And the Doppler effect works for all kinds of waves. Sound waves, light waves, virtually any wave, I guess. However, we're going to look at it specifically in terms of sound waves. So, what exactly is the Doppler effect? Well, in order to appreciate it, what it is it's a, very simply put, it's a shift in perceived frequency due to the motion of the sound source, the thing that's making the noise. If it's moving while it's making the noise, it actually changes the way you hear it. So, let's take a simple example of an object. Very commonly we use a car. Cars move, so let's make noise. So here, let's just draw ourselves on the car. And we'll say that the car is stationary. It's not moving, it's parked. Now, the car is going to make a noise. The noise of the car engine is kind of not a very good noise because it's variable and weird. So we're going to think about the car sounding the horn. The car horn is going to be blowing, but it's going to blow a constant noise as the car is driving. If the driver sounds the horn, then the waves of the horn will sound at a particular frequency. Perhaps they'd be around, I read somewhere that car horns typically are in the key of F for some reason. I'm not sure why, but the note F is probably somewhere around 500-600 hertz or something like that. So let's say there's a frequency of, so the horn frequency is going to be, let's say 600 hertz. What that means is sound waves will be emitted in all directions from the car. So I'm going to represent those sound waves as just little waves like this, pressure waves in the air. Now they will go in all directions, up, down, left, right, in a sphere outward from the car. But we are going to be looking specifically at the ones that are moving along the same plane or line as the car's motion. So the ones that are going up and down won't be affected because the car is not going to move up and down. It's only going to move along the x-axis sideways. So from now on, we're just going to draw the sideways version. So let me draw another picture over here of the same car. But this time, the car will be moving this way with a velocity of 20 meters per second. Well, if you recall when we talked about the airplane, the jet fighter, and how as it moves through the air, it catches up with the sound that it makes. And if it goes the speed of sound, it builds up a huge pressure front in front of it that we call the sound barrier. Remember that? A car doesn't move quite as fast as sound, so it's not going to go to that effect. But what's going to happen is as it moves this way, and as it catches up to the sound that it's making, or not catches up, but that sound is going to be escaping at a lower rate, I guess you could say. It's going to cause the waves to get bunched up. They're going to be emitted closer together. Whereas the waves in the back, because each time the car makes a sound or makes a pressure wave, it's moved away from it, they're going to be stretched out. So we get kind of a stretching of the waves behind the car in the opposite direction. And we get kind of a compressing of the waves. Well, if you compress the waves, you change the frequency, because remember the frequency is how quickly these crests or these compressions are hitting you. And so the waves in the direction of the car's motion are going to be compressed, and the waves opposite that, in the opposite direction, are going to be stretched. So let's see what would happen then if we had car over here moving this way at 20 meters per second, making its horn sound with a frequency. Now I'm going to call that frequency F0 or F naught. F naught, which would be the frequency that the car normally makes when it's standing still. And we said that was 600 hertz. But if you happen to be standing over here, and the car, of course, is traveling along the ground towards you, those pressure waves in front of you will be squished up because of the car's motion. And you will not hear 600 hertz. The ones in the back will be spread out, but they don't matter. The car is coming towards you, and you're going to hear squished up pressure waves in front of the car. And so the way we deal with that is by using this little equation. The frequency that you will hear, the perceived frequency, right? We'll call it F1, will be equal to the original frequency, F0, times the speed of sound in the air, divided by the speed of sound in the air minus the speed of the object. And this little equation will help us figure out what the new frequency would be, what we would hear. So you might want to make a little note here that this is the original, maybe the little o could stand for original frequency, and this stands for the perceived frequency, or what you would hear because of the crunching up of the waves in front of you. So let's do the math. We don't know what F1 is, we're going to figure that out. But the original frequency is 600 hertz. And then the speed of sound. Well, we'll use our standard number of 340 meters per second, just to avoid any complications with temperature and all that. Theoretically, you could have a temperature given in the question, and you would have to figure out the speed of sound using that temperature equation, but probably not. So 340 is our standard speed of sound in regular room temperature air. And then we would have 340 on the bottom minus the speed of the object, which is 20 meters per second. So it's really not super hard math, right? So if we do the math, we would have to take 600 times the 340, which is a fairly big number. And we get 204,000 on top. And then that will be divided by 320. So the answer would be 637.5 hertz. So you see how it's a bigger number. The original hertz, the car horn is actually 600 hertz, but because the car is moving towards you and squishing up the waves as it comes, you're going to hear a horn of 637.5 hertz, a slightly higher frequency sound, a higher pitched sound. Now let's think about the next scenario when the car passes. So now the car has passed you by, and it's over here, right? But it's still going this way at 20 meters per second. And it's still sounding its horn with a frequency of 600 hertz. But because it's moving away from you, these were stretched up. The sound waves behind you are stretched out, or behind the car. So you will hear a different sound again. This time, you will hear a sound that is lower in frequency. And the way we figure that out is by adjusting our little formula ever so slightly. The perceived sound, or the sound that you will hear, is the original frequency times the speed of sound, same on the top, but the bottom is going to be the speed of sound plus the speed of the object, the speed of the car that's moving. So we change it to a plus sign, and that's the only difference. And if we figure it out, we would get F1 equals, again, 600 times 340. Only this time it would be 340 plus 20. So we can borrow our numbers on top. It's the same number as before, 204,000. This time we'll be dividing by not 320, but 360. And if we do that, let's see what we can get here. 566.7-ish hertz. So you can see that we have a lower sound. And this is why, when you're standing somewhere, imagine you're at NASCAR, where the cars actually make this high-pitched whining noise from their engines, you know? As they go by. And if you're standing there, and as the cars go around the track, as they come by, they have a higher pitched sound because they're approaching you. But as soon as they pass you, you hear this. Right? The sound drops off in pitch as the car goes by because it's going from a compressed sound that is higher than usual, and then once it passes you, it's going down to another frequency which is lower. I can't put those both on the same screen, but it's quite a bit lower. And this is why a train, anything that you hear, the whistle of the train, makes that drop in pitch as it passes by you. And that's because it's shifting from approaching you to moving away from you. So we generally write the two equations together in this form. We generally say that the perceived frequency, F1, or whatever you want to call it, will be the original frequency times the speed of sound. And then on the bottom, we put speed of sound plus or minus the speed of the object. And we remember that the minus is if the object is approaching, and the plus is if the object is receding or moving away. And then it becomes a reasonably simple situation. Okay. Now, there is a difficult question that can be asked. It's a little bit more than this plug-and-play type of scenario. And this is a commonly used question in a lot of different tests. So let me set up, this is kind of like the level 3 or 4 version of this, okay? Let's imagine a car starts off here, and it's moving with a speed of v. We don't know the speed. And you're going to be standing sort of on the side of the road right here. And the car is going to travel to you and then away from you. And then over here, as the car goes away, still going at speed v, what we're going to say is that the frequency, if the frequency of the sound, the perceived sound, what you're listening to, that means, drops by 20%. What is the speed of the car? What is the speed of the car? So this question is going to require us to do a couple of things. We'll notice that when the car is approaching us, on this side we have the scrunched up, compressed sound. So while the car is approaching us, we would hear a sound higher than whatever its original frequency was. But then later, we will, as the car goes away from us, the sound waves will be stretched out. So we hear, right? We would hear the car sound quieter on the way away from us. So we kind of have to do two Doppler shifts in one. When the car is right here in this position, it's not moving away or it's not moving towards us at that moment. We're right beside it. It would have the normal, ordinary frequency that it usually has. So what I'm going to do is I'm going to put some frequencies on here. I'm going to call this this would be the sound of the original frequency, unshifted, because the car is not moving towards me or away from me, remember? And so over here, I'm going to call this the F1 frequency. And over here, I'm going to call this the F2. F2 should be quite a bit lower than F1. And what we're going to try to do is come up with something that will allow us to figure out the speed of the car. And of course, we'll use our speed of sound as 340 meters per second. So, let's think about the two Doppler shifts that we could write. We could write the first Doppler shift using the original frequency in F1, like this. F1 equals original frequency times the speed of sound divided by the speed of sound, and I'm going to use minus because in this case the car is approaching, minus the speed of the object. But I don't have much to plug into that, but that is the relationship I would use, right? That describes what's happening on the left side of the picture. On the right side of the picture we have another equation, and that would be the perceived frequency, F2, would be the original frequency of the car times the speed of sound minus this, or divided by the speed of sound. This time I'll use plus VO because the car is receding, we're moving away. Now I have one little bit of information that this question is giving me, and it's this 20% reduction. If the sound drops by 20%, that's like saying that after it passes, the frequency that it has when it passes is only 80% of what it was when it started, right? So we need to come up with a way to say that the frequency after F2 is only going to be 80% of the original frequency F1. And we can do that, I'll do it in a different color, like this. We can say that F or 0.8 of the original frequency, this is kind of like when we did the bouncing ball, right? Equals F2. So the frequency that we hear over here after it passes us is only 80% of what it was when it was approaching us because it's dropped by 20%. The drop has to be taken off. You can't use 20% in the equation. You have to always use how much is left over. So, let's substitute these expressions that we did here for F1 and F2 into this equation. And I'll change to a different color at this point, just because it's fun. So now, we would have 0.8 multiplied by all the stuff above that F1 was equal to. The original frequency times the speed of sound divided by the speed of sound minus the speed of the object. So far, so good, right? Then, on the other side, we still have the original frequency times the speed of sound divided by the speed of sound plus the speed of the object. All right, let's see if we can't do some mathematical messing around with this. The first obvious thing we can do is multiply the 0.8 into the top of that expression. That makes it a tad simpler. Now, what I'm going to do is I'm going to use my rules of math here. And I realize I can do two things. I can divide both sides by F0, and I'm also going to divide both sides by speed of sound, which means the tops of those equations will become very simple. It'll be 0.8, and then if I'm dividing F0 by F0, it's a 1, right? And then I divide Vs by Vs, it's a 1. So the top of that equation just becomes 0.8. Is everybody okay with that? It's a little trickier when you're dividing with fractions, right? But when you're dividing from the numerator. So now I do the same with the other side, and I get 1 F naught divided by F naught is 1, Vs divided by Vs is 1, so 1 times 1 is 1. And on the bottom I get Vs plus V0. Okay, well now what I'm going to do is I'm going to cross multiply. I'm going to move over here to this side, so we're just going to do this. If I cross multiply my equations, I get 0.8 times speed of sound plus speed of object equals speed of sound minus speed of object. So all that mess simplified into something very simple, didn't it? It simplified into three terms. This one, which represents the percentage of the sound remaining. So if I did a different question and it said it dropped by 30%, I could just use 0.7 here, right? So you can use any percentage in this place. And then we have these two terms, which are pretty straightforward terms. Don't forget, we know that the speed of sound in the air is 340 meters per second. So if we plug that into the equation, the only thing left is VO, which is the speed of the object. So let's do that. Let's put the 340 in there. So it will become 0.8 times 340 minus VO. Sorry, I think it's plus. Let's double check. It's plus on that side, right? Yeah. You can remember that the percentage goes with the plus, because they both start with P. Percentage goes with the plus. Equals 340 minus VO. So if we multiply 0.8 times this, let's see, what do we get here? 4 8s are 32, 3 8s are 24, so I think we get 272, am I right? Somebody double check my math as we go. 0.8 v 0. And now we can just group the like terms. So we'll put all of these on this side. If I move that one over, it becomes positive. And then if I move the 372 over, it becomes negative 272, sorry. So this is 0.8 plus 1 is 1.8, right? And then over here, if we take 272 away from 340, what are we left with? 272, take away 340, take away 272. 68, right? So 68. And then we divide 68 divided by 1.8. What do we get? Where'd you go? Sorry? 37.8 meters per second is how fast the car must be going in order for that to happen. So now that we've done this together, we've examined this scenario, we've actually created a shortcut for ourselves. If we had to, I suppose, and we knew what we were doing and we studied hard, we could start here and we could start all the way back here, write the two expressions and write in all the stuff that we did. But we know that since we did that without any numbers really, it's always going to end up bringing us to here. Whoops. It's always going to end up bringing us to here. So this little expression is a shortcut. As long as we remember what number to put up front. You have to remember that it's the percentage that's remaining after the shift from going from passing in person, but the other parts don't change. So this could be a shortcut formula for a question like this one, instead of going back and doing all that algebra again. We have this little shortcut to get the speed of the car. And that's basically the Doppler effect.